There is a number written into the fabric of reality itself. It is not carved on any stone. No ancient civilization left it behind. Yet this number controls everything. Every beam of starlight that crosses the void between galaxies obeys it. Every photon dancing across your skin right now submits to its rule. This number is 299,792,458 meters per second. That is the speed of light. And tonight, as you settle into the quiet darkness, we are going to explore a mystery that haunted one of the greatest minds who ever lived. Why is this number the limit? Why can nothing in the entire universe travel faster? What Richard Feynman uncovered about this question will melt your mind. And by the time we reach the end of this journey, you will never look at a simple ray of light the same way again. If these peaceful explorations help you unwind or spark your curiosity, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. Now let yourself sink a little deeper into wherever you are resting. Let your breathing slow. We have a long and beautiful path ahead of us. The speed of light has puzzled humanity since we first noticed the stars. For most of our history, people assumed light was instant. You light a candle, and the room fills with glow immediately. You watch lightning strike on a distant hill, and you see the flash at the very moment it happens. Or so it seems. The idea that light needed time to travel from one place to another seemed absurd for thousands of years. After all, what could possibly be faster than seeing? Yet the universe had a secret hidden in plain sight. Light is not instant. It moves, and it moves at a very specific speed that never, ever changes. The first person to seriously measure this cosmic speed limit was a Danish astronomer named Ole Rømer back in the 1670s. He was studying the moons of Jupiter, those little worlds that dance around the giant planet in predictable patterns. Rømer noticed something strange. The timing of the moon's eclipses, when they pass behind Jupiter, seemed to shift depending on where Earth was in his orbit. When Earth was closer to Jupiter, the eclipses came a little early. When Earth was farther away, they came a little late. Most astronomers shrugged this off as measurement error, but Rømer saw something deeper. He realized that light must take time to travel across the extra distance when Earth was on the far side of its orbit. By calculating how much the timing shifted and how much farther the light had to travel, he estimated the speed of light for the first time in human history. His number was not perfectly accurate by modern standards, but it was remarkably close. And more importantly, it proved that light was not instant. It was a traveler moving through space, just like everything else. This simple discovery would eventually lead to one of the strangest and most beautiful insights in all of physics. But that would take another 200 years, and a mind unlike any other. For now, just know that from this moment on, whenever you see light, you are seeing the past. The light from the lamp across the room left that lamp a tiny fraction of a second ago. The light from the moon left its surface about 1¼ seconds ago. The light from the sun departed 8 minutes ago, and the light from the nearest star beyond our sun has been traveling for over 4 years. You never see the universe as it is right now. You only see it as it was, frozen moments preserved in the beams of light that finally reach your eyes. Let that thought settle over you like a gentle blanket. We live surrounded by the echoes of the past. Every glance out your window is a glimpse backward through time. The farther you look, the deeper into history you peer. And all of this is possible because light has a speed, a limit, a cosmic boundary that nothing can cross. But why does this limit exist? Why specifically 298,792,458 meters per second, and not some other number? Why not faster? Why not slower? Why any speed limit at all? These questions troubled physicists for centuries, but it was not until a young patent clerk in Switzerland began daydreaming about chasing beams of light that the answers started to emerge. His name was Albert Einstein, and his thoughts about light would shatter our understanding of time, space, and reality itself. Imagine you are on a train, not just any train, but a train traveling at nearly the speed of light. You are sitting in your seat, watching the world blur past the windows at impossible velocities. Now imagine you turn on a flashlight and shine it toward the front of the train. From your perspective inside the train, the light shoots forward at its normal speed. It zooms away from your flashlight at 209,792,458 meters per second, just like light always does. But here is the puzzle that kept Einstein awake at night. What does someone standing on the platform outside the train see? To them, the train is already hurtling forward at nearly the speed of light. So when you shine your flashlight forward, shouldn't the light from your flashlight move at the train's speed plus the light's own speed? Shouldn't it appear to travel at nearly twice the speed of light? According to the physics people knew before Einstein, the answer should be yes. Speeds should add together. If you throw a ball forward from a moving car, the ball's speed from an outside observer's view is the car's speed plus the ball's speed. Simple addition. But light does not play by those rules. When scientists measured the speed of light coming from moving sources, they found something shocking. The light always traveled at exactly the same speed. It did not matter if the source was racing toward you or away from you. It did not matter if you were standing still or sprinting. Light always arrived at precisely 299,792,458 meters per second. Never faster, never slower. Always exactly the same. This seemed impossible. It defied common sense. It broke the simple math of adding speeds together. But the experiments were clear. Light refused to change its speed no matter what. Einstein realized that if the speed of light was truly constant for all observers, then something else had to give. If light could not change, then the things we thought were unchangeable must be the ones that bend. And what are those things we thought were solid and fixed? Time and space themselves. This is where the journey becomes dreamlike. Let your mind relax and follow along without grasping too tightly. What Einstein discovered is that time is not the same for everyone. A clock on that speeding train does not tick at the same rate as a clock on the platform. Time itself stretches and compresses depending on how fast you are moving. This is not a trick. It is not an illusion. It is the actual physical truth of our universe. Time passes differently for different observers, and this effect becomes more pronounced the faster you travel. At everyday speeds, the difference is too tiny to notice. A clock in a car moving down the highway runs only a trillionth of a second slower than a clock standing still. You could never feel such a tiny difference in a human lifetime. But as you approach the speed of light, the effect grows enormous. At 90% of light speed, time on the moving object runs about twice as slow. At 99%, it runs about 7 times slower. And at 99.99999%, time nearly stops altogether. This is not science fiction. We have measured this with atomic clocks flown on jets. We see it in the particles that rain down on Earth from space. Time dilation is real. It is happening right now to the satellites orbiting overhead. Without correcting for it, the GPS system that guides your phone would drift off by miles within a day. So here is the first piece of the puzzle about why light speed is the limit. As any object with mass approaches light speed, Time for that object slows down from an outside perspective, but it takes energy to accelerate. And as you get closer and closer to light speed, something strange happens to your mass. Not your rest mass, the mass you have when sitting still, but your effective mass, the mass that determines how hard you are to push. This effective mass increases as your speed increases. At 90% of light speed, you act like you have about twice your normal mass. At 99%, you act like you have about 7 times your normal mass. At 99.99%, you act like you have over 70 times your normal mass. Do you see where this is going? The closer you get to light speed, the heavier you effectively become. The heavier you become, the more energy it takes to accelerate you further. And as you approach light speed itself, your effective mass approaches infinity. It would take infinite energy to push any object with mass all the way to the speed of light. Infinite energy is not something the universe contains. It is not something that can exist. Therefore, nothing with mass can ever reach the speed of light. The limit is not just a rule. It is a mathematical certainty. It is built into the equations that govern how energy and mass and velocity interact. But wait, light travels at light speed. How does it get away with breaking this rule? The answer is beautiful in its simplicity. Light has no mass. Photons, the particles of light, have zero rest mass. They are pure energy, moving through space. Because they have no mass, they are exempt from the infinite energy requirement. They do not need to be accelerated to light speed. They are born traveling at light speed. From the very instant a photon pops into existence, it is already moving at 299,792,458 meters per second. It cannot go slower. It cannot go faster. It simply exists at that speed, or it does not exist at all. This is one of the strange properties of being massless. If you have no mass, you must travel at the speed of light. If you have any mass at all, no matter how tiny, you can never reach the speed of light. There is no middle ground. There is no almost. The division is absolute. Mass means slower. Massless means light speed exactly. Nothing else is possible. Now let that sink in as you rest. Every beam of light that has ever existed has traveled at exactly the same speed. The light from the first stars 13 billion years ago moved at this speed. The light from the reading lamp beside your bed moves at this speed. The light that will shine from the last stars when the universe grows old and cold will move at this speed. It is one of the great constants of nature, unchanging, eternal, written into the structure of reality like a law that cannot be broken. But we have only scratched the surface of why this matters. The speed of light is not just the fastest anything can go. It turns out to be something far more fundamental. It is the speed of causality itself. Every cause and every effect in the universe is connected by influences that travel at or below this speed. Nothing can affect anything else faster than light can travel between them. This means that the speed of light determines the very structure of time and sequence in our cosmos. Imagine two events happening far apart in space. Maybe a star explodes on one side of the galaxy and a planet forms on the other side. Whether these events can influence each other depends entirely on whether light has had enough time to travel between them. If the distance is too great and the time too short, those events are causally disconnected. Neither one can have caused the other. They exist in their own separate bubbles of reality, unable to touch. This is what Einstein meant when he said that nothing can travel faster than light. He did not just mean spaceships and rockets. He meant information, influence, causality itself. If you could send a message faster than light, You could create paradoxes that break the logic of cause and effect. You could potentially send information backward in time. The math shows this clearly. Faster than light travel in one reference frame looks like backward time travel in another reference frame. The universe seems to have a deep prohibition against this. And that prohibition takes the form of the speed of light as an ultimate barrier. We have now covered a lot of ground. You understand that light has a speed. You understand that this speed is constant for all observers. You understand that as objects approach this speed, time dilates and effective mass grows. You understand that only massless things can travel at exactly light speed, and that everything else must remain below. You understand that this speed represents the speed of causality, the maximum rate at which any influence can propagate through the universe. But there is still so much more to discover. We have talked about what the speed of light does. We have talked about why nothing can exceed it, but we have not yet explored what light actually is. And this is where Richard Feynman enters our story. This is where the mystery deepens into something even more strange and wonderful than what we have seen so far. Feynman did not just accept the rules about light. He dug beneath them. He asked questions that seemed almost childish in their simplicity, but led to answers that transformed physics forever. Richard Feynman was born in 1918 in New York City. From a young age, he had an unusual relationship with the world. He was endlessly curious, but not in the way of a collector gathering facts. He wanted to understand things from the ground up. He wanted to rebuild every idea from scratch to make sure it really made sense. His father taught him to question everything, to look past the names we give things and examine what is actually happening underneath. This approach would serve Feynman well as he grew into one of the most original thinkers physics has ever produced. By the time Feynman was working on his doctorate, the physics community was struggling with a serious problem. The theory of quantum mechanics, which described how particles behave at the smallest scales, did not fit together properly with the theory of special relativity, which described how things behave at high speeds. Light was at the center of this confusion. Quantum mechanics said that light came in packets called photons. Relativity said that light always traveled at the same speed, and that this speed was built into the structure of space and time. But when physicists tried to combine these ideas mathematically, they kept getting nonsense answers. Infinities appeared everywhere. The equations predicted that simple quantities like the mass or charge of an electron should be infinite, which was clearly wrong. Feynman, along with two other brilliant physicists named Julian Schwinger and Shinichiro Tomonaga, found a way out of this mess. They developed what is now called quantum electrodynamics, or QED for short. This theory describes how light and matter interact at the quantum level. And at the heart of QED is a strange and beautiful picture of how light actually travels from one place to another. In Feynman's picture, light does not simply travel in a straight line from point A to point B. Instead, you have to consider every possible path that light could take. Every single one. The straight path, yes, but also paths that curve wildly, paths that loop around, paths that zigzag back and forth, paths that go to the edge of the universe and back. Every conceivable route contributes to what actually happens when light goes from here to there. This might sound insane. How could light possibly take every path at once? But this is how the quantum world works. At the smallest scales, particles do not have definite paths like a ball rolling across a table. They exist in a kind of blur of possibilities. All paths happen simultaneously, and they interfere with each other like waves in a pond. Some paths reinforce each other, others cancel out. The pattern of reinforcement and cancellation determines the probability of where the light will actually end up. The amazing thing is that when you add up all these crazy paths, the ones that contribute most strongly are the ones closest to the straight line. The wild detours mostly cancel themselves out. What remains is light traveling along more or less the classical path, but with tiny quantum corrections that make the theory incredibly precise. QED makes predictions that have been verified to something like 10 decimal places. It is one of the most accurate theories humans have ever created. But Feynman did not present this theory using heavy mathematics alone. He invented a visual language, a way of drawing pictures that captured what was happening in these quantum interactions. These are now called Feynman diagrams. In a Feynman diagram, straight lines represent particles like electrons. Wavy lines represent photons. Points where lines meet represent interactions. Moments when particles emit or absorb light. These simple drawings encode incredibly complex mathematics, and they changed how physicists think about the subatomic world. What Feynman's work revealed about light is profound. Light is not just a wave rippling through space. It is not just a particle flying from one place to another. It is something stranger that includes both descriptions and transcends them. When you shine a flashlight, you are launching countless photons, but each photon does not take a single path. In some deep sense, it takes all paths. The reason light behaves so predictably at large scales, traveling in straight lines and bouncing off mirrors at equal angles, is because of how all these quantum paths interfere with each other. Order emerges from the sum of infinite possibilities. Let your eyes grow heavier as you consider this. The light filling your room right now is a symphony of quantum possibilities, all playing together to create the simple brightness you perceive. Beneath the calm surface of everyday experience lies a realm of unimaginable complexity. And yet it all works together perfectly. The equations balance. The predictions match reality. The universe somehow computes all these infinite paths and produces the coherent light that guides your way through the darkness. Feynman had a gift for finding the playful in the impossible. Where other physicists saw intimidating walls of equations, he saw puzzles to be cracked, games to be played. He once said that the first principle is that you must not fool yourself, and you are the easiest person to fool. This honesty with himself allowed him to approach problems with fresh eyes. He was not content to simply learn the standard methods and apply them. He had to truly understand what was going on. And this drive to understand led him to insights that others had missed. One of Feynman's great contributions was showing how the speed of light emerges naturally from the deepest principles of physics. In QED, the speed of light is not just a measured number plugged into the equations. It appears because of how space and time work together, how causality operates, how symmetry constrains what is possible. The speed of light is the conversion factor between space and time. 1 second of time corresponds to about 300,000 kilometers of space. These are the same thing measured in different units, just as inches and centimeters are the same length measured differently. This might seem like a strange claim. How can time and space be the same thing? They feel so different to us. We can move freely through space in any direction we choose. We can walk north, south, east, or west. But time seems to push us inexorably forward. We cannot turn around and walk back to yesterday. Yet relativity shows that this difference is partly an illusion of our slow-moving perspective. At speeds close to light, time and space mix together. Movement through space affects the passage of time. What one observer calls space, another observer calls a mix of space and time. They are woven together into a single fabric called spacetime. The speed of light is the stitch that holds this fabric together. It is the ratio that tells you how much space corresponds to how much time. And because it is a ratio built into the very structure of spacetime itself, it cannot change. It is not a property of light. It is a property of reality. Light just happens to move at this fundamental speed because it is massless. Other massless things, like the theoretical particles called gravitons that would carry the force of gravity, would also have to travel at exactly this speed. The speed of light should really be called the speed of causality, or the speed of spacetime. Light simply rides along this universal speed limit because it has no mass to hold it back. This is one of the deep insights that Feynman helped establish. The laws of physics look the same to all observers moving at constant speeds relative to each other. This is called Lorentz invariance, after the physicist who first wrote down the mathematical transformations. And Lorentz invariance requires that there be a universal speed limit. You cannot have observers who all see the same laws of physics without having a speed that everyone agrees on. That speed is the speed of light. It has to exist for reality to be consistent. Think about this as you drift towards sleep. The universe requires a speed limit not because of some arbitrary rule, but because without it, the laws of physics would become contradictory. Different observers would see different laws. Cause and effect would become jumbled. The orderly progression from past to future would dissolve into chaos. The speed of light is the price we pay for a universe that makes sense. And given that choice, the cosmos has decided that making sense is worth the trade. Let us now journey deeper into the nature of light itself. We have spoken of photons and quantum paths. We have spoken of spacetime and causality. But there is another layer to this mystery that takes us into even stranger territory. Light is electromagnetic radiation. It is a ripple in the electromagnetic field that permeates all of space. And this field is one of the most fundamental aspects of our universe. Imagine space not as empty void, but as filled with an invisible field that stretches everywhere. At every point in the universe, this field exists. Most of the time, it sits quietly at zero. But when something disturbs it, ripples spread outward. Those ripples are light. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. These two fields bootstrap each other, pushing the disturbance forward at exactly the speed of light. The wave keeps itself going, leapfrogging from electric to electric again, racing through the void forever unless something absorbs it. This picture was first assembled by the Scottish physicist James Clerk Maxwell in the 1860s. He wrote down 4 equations that describe how electric and magnetic fields behave and interact. When he combined these equations, something unexpected fell out. He found that they predicted waves that would travel through space at a specific speed. And when he calculated that speed from the fundamental constants that appeared in his equations, he got a number that matched the known speed of light almost exactly. Maxwell had discovered that light is an electromagnetic wave. The colors we see, the warmth we feel from the sun, the radio waves that carry music to our speakers, the X-rays that peer through our bodies, the gamma rays born in nuclear explosions, these are all the same thing. They are all electromagnetic waves, differing only in their wavelength and frequency. Red light has longer waves than blue light. Radio waves have much longer waves still. Gamma rays have waves shorter than atoms, but they all travel at the same speed through empty space, always and forever at 299,792, 458 meters per second. Maxwell's discovery was one of the great unifications in physics. Before him, Electricity, magnetism, and light seemed like three separate phenomena. After him, they were revealed as different aspects of the same underlying reality. This kind of unification, showing that things we thought were different are actually the same, is one of the deepest goals of physics. And it has continued ever since Maxwell's time. Today, we know that electromagnetism is unified with the weak nuclear force. Some physicists suspect that all the forces of nature may ultimately be unified into a single framework, but that is a journey for another night. For now, let us return to Maxwell's waves and ask a simple question. Why do these waves travel at this particular speed? Where does the number come from? Maxwell's equations contain two fundamental constants. One is called the permittivity of free space, usually written as epsilon naught. It describes how easily electric fields can form in empty space. The other is called the permeability of free space, usually written as mu naught. It describes how easily magnetic fields can form in empty space. When you combine these two constants in a certain way, taking 1 over the square root of their product, you get the speed of light. The formula is simple and beautiful. The speed of light equals 1 divided by the square root of epsilon naught times mu naught. That is it. Two fundamental properties of empty space, combined together, give you the cosmic speed limit. The speed of light is not set by light. It is set by space itself. It is determined by how easy it is for electromagnetic fields to exist in the vacuum. This tells us something profound. The speed of light is not really about light. It is about the nature of the vacuum. It is about the properties of empty space. Change those properties, and you would change the speed limit. But the properties of empty space seem to be the same everywhere we look. The vacuum is uniform. Its permittivity and permeability do not vary from place to place or from time to time, at least as far as we can measure. So the speed of light is the same throughout the observable universe, now and in the distant past, here and in the most remote galaxies. Rest in this thought. The emptiness between the stars is not really empty. It is a medium with definite properties. It has a stiffness that determines how fast ripples can spread, and that stiffness is perfectly tuned to give us the universe we inhabit. If the vacuum were different, if space itself had other properties, everything would change. The size of atoms, the strength of chemical bonds, the stability of matter itself, all of these depend on the fundamental constants that determine the speed of light. We live in a universe precisely calibrated to produce stars and planets and life, and the speed of light is one thread in that intricate tapestry. Now let us turn to one of the strangest consequences of all this. We have said that nothing with mass can reach the speed of light. But what happens as you approach it? What would you experience if you were aboard a spaceship accelerating closer and closer to that ultimate barrier? From your perspective inside the ship, everything would feel normal. You would sit in your chair, drink your coffee, read your books. Time would seem to pass at its usual rate. Your heartbeat would feel steady. Your clocks would tick regularly. You would not feel anything strange at all. This is one of the key insights of relativity. You cannot tell how fast you are moving in any absolute sense. All motion is relative. Inside your ship, with the windows covered, there would be no experiment you could perform that would reveal your speed. The laws of physics work exactly the same at any velocity, but if you looked outside, you would see something remarkable. The universe would appear compressed in the direction of your motion. Stars ahead of you would seem closer together, bunched toward the front. Stars behind you would seem farther apart. This is called length contraction, and it is the companion effect to time dilation. Just as time stretches at high speeds, space contracts. The distances in front of you would shrink, while the distances behind you would expand. Even stranger, the colors of the stars would shift. Stars ahead of you would appear bluer than normal. Stars behind you would appear redder. This is the relativistic Doppler effect. As you race toward a light source, the waves pile up, making them shorter and bluer. As you race away, the waves stretch out, making them longer and redder. At speeds very close to light, this effect becomes extreme. Stars directly ahead might shift from visible light into X-rays or even gamma rays. Stars behind might drop from visible light into radio waves. The universe would glow differently depending on which direction you looked. And then there is time. From your perspective, time on the ship passes normally. But from the perspective of someone watching from Earth, time on your ship has slowed dramatically. If you travel at 99% of light speed, only 1 year might pass for you while 7 years pass on Earth. If you travel at 99.99%, only 1 year might pass while 70 years pass on Earth. The faster you go, the more extreme the difference becomes. This leads to what is sometimes called the twin paradox. Imagine two twins. One stays on Earth. The other boards a spaceship that travels to a distant star at nearly the speed of light and then returns. When the traveling twin arrives back home, they have aged only a few years, but their sibling who stayed on Earth has aged decades. They were born at the same moment, but now one is old and the other is still young. This is not a paradox in the sense of being impossible. It is simply counterintuitive. We are not used to time working this way because we never move fast enough to notice. But the effect is real. It has been verified with precise atomic clocks. Time genuinely passes more slowly for things that move faster. And this means that the speed of light is not just a limit on how fast you can travel through space. It is a limit on how fast you can travel through time. You see, we are always moving through space-time. Even when you sit perfectly still, you are moving through time at the maximum possible rate, 1 second per second. When you start moving through space, some of your motion through time gets diverted into motion through space. The faster you move through space, the slower you move through time. At the speed of light, all your motion would be through space and none through time. This is why photons do not experience time at all. From the perspective of a photon, it is emitted and absorbed at the same instant, no matter how far it travels. Billions of years might pass for us, but for the photon, there is no duration. It exists in an eternal now, frozen at the boundary of time itself. Let this strange thought carry you deeper into relaxation. You are a being trapped in the slow stream of time, watching the universe unfold moment by moment. But photons exist outside this stream. They connect the past to the future instantaneously from their own point of view. Every photon that strikes your eye has existed in a kind of timeless state, even though years or centuries may have passed from your perspective. Light is the bridge between moments. It carries information across time while experiencing no time itself. Feynman understood these connections deeply. He had a way of holding multiple perspectives in his mind simultaneously, seeing the same physics from different angles. He could talk about light as a wave spreading through space, light as a particle following quantum paths, light as a manifestation of electromagnetic fields, light as a messenger connecting events in space-time. All these descriptions were true simultaneously. None was complete by itself. The full truth required all of them woven together. This is one of the great lessons of modern physics. Reality is too rich to be captured by any single description. We need multiple languages, multiple frameworks, multiple ways of seeing. The wave picture is useful for some questions. The particle picture is useful for others. The field picture is useful for still others. A master physicist moves fluidly between these descriptions, using whichever one best illuminates the problem at hand. Feynman was a virtuoso at this, switching perspectives in mid-thought, finding connections that others had missed. But Feynman also knew the limits of human understanding. He famously said that nobody understands quantum mechanics. He did not mean that the math was too hard, or that the predictions were unclear. The math was well established, and the predictions were astonishingly accurate. What he meant was that our intuitions, built for the world of rocks and trees and human-scale objects, simply cannot grasp what is happening at the quantum level. We can calculate, we can predict, we can use quantum mechanics to build lasers and transistors and GPS satellites. But we cannot truly picture what a photon is doing when no one is looking. This is humility in the face of nature. The universe is not obligated to make sense to us. Our brains evolved to find food and avoid predators on the African savanna. They did not evolve to understand the quantum vacuum or the structure of space-time. That we can understand as much as we do is a kind of miracle. But there are depths we may never reach, mysteries that may never yield to human comprehension. And perhaps that is okay. Perhaps the honest response to the universe is wonder, not certainty. Let that wonder fill you now. You are a collection of atoms that somehow learn to contemplate atoms. You are matter that ponders matter. You are the universe looking back at itself and asking why. And one of the greatest mysteries you can contemplate is the one we have been exploring tonight. Why is there a speed limit? Why can nothing exceed the speed of light? The answer touches on the deepest foundations of reality. It connects space, time, mass, energy, causality, and information into a single coherent picture. And at the center of that picture is a number, 299,792, 458 meters per second. Now let us go even deeper. We have talked about why the speed of light is the limit. We have talked about what light is. We have talked about Feynman and quantum electrodynamics. But there is another dimension to this mystery that we have not yet explored. What does the speed of light mean for the structure of the universe itself? How does it shape the cosmos we observe? The answer begins with a concept called the observable universe. This is not the whole universe. It is just the part we can see. And the reason we can only see part of the universe is because light has a finite speed and the universe has a finite age. The universe is about 13.8 billion years old. Light travels at the speed of light. So you might think that we can see about 13.8 billion light years in every direction. But the actual answer is stranger. The observable universe stretches about 46 billion light years in every direction. How can this be if the universe is only 13.8 billion years old? Surely light has not had time to reach us from 46 billion light years away. The answer is that space itself has been expanding. When light left a distant galaxy billions of years ago, that galaxy was much closer to us. The light has been traveling through space ever since, working its way toward us. But while the light was traveling, the space between us and that galaxy was stretching. The galaxy has been carried away from us by the expansion of space itself. By the time the light finally arrives at our telescopes, the galaxy that emitted it is now 46 billion light years away, even though the light only traveled for 13.8 billion years. This expansion of space is not like objects flying apart through space. It is space itself stretching, like the surface of a balloon being inflated. Galaxies are not really moving through space away from us. They are being carried along as the space between us and them grows. And this expansion is happening everywhere, in every direction, at every moment. The farther away something is, the faster it appears to recede from us, because there is more space between us and it, and all that space is expanding. Here is where things get truly strange. The expansion of the universe is accelerating. Distant galaxies are not just moving away from us. They are moving away faster and faster as time goes on. This acceleration is driven by something we call dark energy, a mysterious component of the universe that pushes space to expand ever more rapidly. We do not know what dark energy is. We only know that it is there, filling empty space with a gentle but relentless outward pressure. Because of this accelerating expansion, there are galaxies that we can see, but that we will never be able to reach, even if we could travel at the speed of light. The space between us and them is growing faster than light can cross it. These galaxies are beyond our cosmic horizon. They will eventually fade from view as their light is stretched into invisibility by the expansion. The observable universe is shrinking, in the sense that fewer and fewer galaxies will remain visible to us as the eons pass. This is one of the most sobering consequences of the speed of light being a limit. We are trapped in a bubble of space-time from which we can never escape. We can see only what light has had time to bring us. We can reach only what the speed of light allows us to touch before the expansion carries it away. The universe is unimaginably vast, but most of it is forever beyond our grasp. Rest in this knowledge. You are a citizen of a bounded realm. Your cosmic neighborhood extends about 46 billion light years in every direction, and that is all you will ever know directly. Beyond lies mystery. Perhaps other pockets of existence, other islands of matter, other civilizations we will never meet. Perhaps patterns and structures we cannot imagine. Perhaps nothing at all. We simply do not know. The speed of light draws a boundary around our experience, and beyond that boundary lies the unknowable. But within that boundary, there is so much to explore. Hundreds of billions of galaxies, each containing hundreds of billions of stars, planets beyond counting, moons and asteroids and comets, nebulae where new stars are born, remnants where old stars have died, black holes where space-time itself is torn and twisted. And through all of this, light carries its messages. Every photon that reaches your eye has a story to tell. It has traveled across time and space to bring you news from somewhere far away and long ago. Feynman reveled in this cosmic perspective. He saw physics not as abstract equations, but as a way of understanding our place in the universe. He often spoke about the beauty of a flower being enhanced, not diminished, by scientific understanding. Knowing how a flower works, how its cells capture sunlight and convert it to energy, how its colors attract pollinators, how its DNA encodes instructions for building petals and stems. None of this makes the flower less beautiful. It adds layers of appreciation. The aesthetic beauty is joined by the beauty of understanding. The same is true for light and the speed limit. Learning that nothing can travel faster than light does not diminish our dreams of exploration. It focuses them. It tells us that if we want to reach the stars, we must think carefully about time and energy and what we are willing to sacrifice. It tells us that the messages we send into the void will take years or centuries to reach their destinations. It tells us that any journey to another star will be a one-way trip for most practical purposes, a permanent farewell to the world you knew. This is not a reason for despair. It is a reason for careful thought. The universe is not built for easy answers. It rewards patience, ingenuity, and courage. Let us now consider some of the dreams humanity has had for exceeding the speed of light, and why they do not work. Throughout science fiction, writers have imagined faster than light travel, warp drives that compress space in front of a ship and expand it behind, hyperspace routes that shortcut through higher dimensions, wormholes that connect distant points like tunnels through a mountain. These ideas are wonderful for storytelling, but do any of them work in reality? The honest answer is that we do not know for certain, but probably not. The warp drive concept, first seriously analyzed by physicist Miguel Alcubierre, requires exotic matter with negative energy density. Such matter has never been observed and may not exist. The energy requirements for even a small warp bubble would be enormous, possibly greater than the energy output of stars. And there are serious questions about whether causality could survive a universe where such travel was possible. Wormholes face similar problems. In theory, general relativity allows for tunnels through spacetime that could connect distant points, but keeping a wormhole open would require exotic matter, just like the warp drive. And even if you could build a wormhole, any matter passing through it might destabilize the tunnel, causing it to collapse before anything could make the journey. Hyperspace, as imagined in most fiction, has no basis in known physics. Our universe appears to have 3 dimensions of space and 1 of time. There may be additional dimensions curled up too small to notice, as some theories suggest. But these tiny dimensions do not offer shortcuts for travel. They are more like decorations on the fabric of space-time than separate rooms to move through. This might seem disappointing. Humans love the idea of zooming between the stars, exploring strange new worlds, boldly going where no one has gone before. But perhaps the limitation is not a curse. Perhaps it is a teacher. The speed of light forces us to think differently about exploration. It encourages us to build self-sufficient ships that could sustain generations of travelers. It encourages us to develop patience as a civilization, planning projects that will take centuries to complete. It encourages us to focus on our own solar system first, on the moon, on Mars, on the asteroids, before dreaming of Alpha Centauri. And who knows what discoveries await within our own cosmic backyard? The moons of Jupiter and Saturn may harbor oceans beneath their icy shells. Mars may still have microbial life hidden beneath its rusty soil. The Kuiper Belt and the Oort cloud are filled with billions of icy bodies we have barely glimpsed. There is enough to explore within the reach of conventional rockets to occupy humanity for thousands of years. The speed of light is a limit, yes, but it is a limit we are nowhere close to reaching anyway. Feynman would probably have enjoyed this perspective. He was deeply skeptical of grandiose claims and quick to puncture pretension. He would have asked uncomfortable questions about faster-than-light schemes. He would have demanded the math. He would have checked the assumptions. And when the answers came back negative, he would not have been dismayed. He would have turned his attention to the puzzles that actually have answers, the mysteries that yield to patient inquiry, the questions that teach us something true. Speaking of mysteries that yield to inquiry, let us explore something that puzzled physicists for decades before Feynman helped solve it. The mystery is this: how do particles of light interact with particles of matter? When a photon strikes an electron, what actually happens? Before quantum electrodynamics, physicists had only rough pictures of this interaction. They knew that light could knock electrons loose from metal surfaces, a phenomenon called the photoelectric effect. They knew that electrons could emit light when they jumped between energy levels in atoms. They knew that light could scatter off electrons, exchanging energy and momentum, but the detailed mechanism was unclear. How did a massless particle of pure energy exchange its properties with a particle that had mass and charge? Feynman's diagrams provided a way to visualize these interactions. In a typical diagram, you might see an electron represented as a line moving through time. Then a wiggly line approaches, representing a photon. Where the wiggly line meets the straight line, there is a vertex, a point of interaction. At that vertex, the electron absorbs the photon and changes its state. Its energy increases, its momentum shifts. The photon disappears, its energy now carried by the electron. This simple picture hides enormous mathematical complexity. To calculate the probability of such an interaction, you need to consider all possible ways it could happen. The photon could be absorbed at any point along the electron's path. The electron could have been doing all sorts of things before and after the absorption. You sum over all these possibilities, accounting for their phases and interference patterns. The result is a precise prediction that matches experimental measurements to extraordinary accuracy. But Feynman did not stop there. His diagrams also showed that more complicated interactions were possible. An electron might emit a photon and then reabsorb it before anything else happens. This is called a virtual photon because it exists only briefly and cannot be observed directly. These virtual photons contribute to the electron's properties. They give the electron a slightly larger magnetic moment than you would expect from simple calculations. They shift the energy levels of atoms by tiny amounts. These shifts have been measured, and they match Feynman's predictions almost perfectly. The world of virtual particles is strange and wonderful. Physicists talk about the vacuum as seething with activity. Pairs of particles and antiparticles pop into existence from nothing and then annihilate each other before they can be observed. Photons are constantly being emitted and absorbed. The quiet emptiness we perceive is actually a buzzing sea of quantum activity, hidden from our direct perception, but leaving subtle traces in every measurement we make. Now, you might wonder how virtual particles relate to the speed of light. After all, if particles are constantly appearing and disappearing, are they violating any rules? The answer is that virtual particles are not real particles in the usual sense. They are mathematical tools for calculating how quantum fields behave. They do not travel from one place to another carrying information. They do not violate causality. They exist in a strange middle ground, neither fully real nor fully imaginary, but essential for making the math work out correctly. The speed of light remains inviolate. Erfaidi, real photons travel at exactly light speed. Real information travels at or below light speed. The quantum foam of virtual particles does not change this. It adds texture to the vacuum, but it does not open shortcuts through spacetime. Feynman's calculations showed this clearly. Quantum electrodynamics respects relativity. The speed of light is built into the theory at the deepest level. Let yourself drift further into relaxation as we explore another facet of Feynman's thinking about light. He was fascinated by the question of why physics works at all. Why is the universe comprehensible? Why do mathematical equations describe the behavior of particles and fields so accurately? This is not a question with an obvious answer. There is no logical reason why the universe should be understandable by beings like us. Yet it is. And Feynman found this deeply mysterious and deeply wonderful. One aspect of this mystery is the unreasonable effectiveness of mathematics. Equations written down by physicists in one context turn out to apply in completely different situations. Maxwell's equations, originally designed to describe electromagnetic phenomena in laboratories, apply unchanged to radio waves from distant galaxies. The Schrödinger equation, formulated to explain atomic spectra, applies to superconductors and Bose-Einstein condensates and phenomena that had not been imagined when it was written. Nature seems to have a mathematical structure that goes far beyond what we would need for everyday survival. Feynman did not claim to have answers to these philosophical puzzles. He was more comfortable with specific calculations than with grand pronouncements about why the universe is the way it is. But he appreciated the questions. He understood that physics touches on issues that philosophy and religion have wrestled with for millennia. Questions about the nature of reality, the origin of order, the place of mind in a material universe. Physics does not answer these questions definitively, but it provides a perspective, a set of constraints, a framework within which any answers must fit. The speed of light is part of this framework. Whatever else the universe may be, it is a place where causes precede effects, where information cannot travel infinitely fast, where the past influences the future, but not the reverse. These are not arbitrary choices. They are necessary for a coherent reality. A universe without such constraints would be a universe of chaos, where anything could happen at any moment, where planning and learning and growth would be meaningless. The speed of light helps make the universe a place where stories can unfold, where patterns can persist, where beings like us can exist and wonder. Now let us shift our attention from the abstract to the practical. The speed of light affects our daily lives in ways most people never notice. The most obvious example is telecommunications. Every phone call, every text message, every video stream travels as electromagnetic waves moving at the speed of light. When you speak to someone on the other side of the world, your voice is converted to electrical signals transmitted through fiber optic cables or bounced off satellites and converted back to sound on the far end. The whole process takes a fraction of a second, but even a fraction of a second matters in some contexts. Online gamers know about latency, the delay between pressing a button and seeing the result on screen. Part of this delay comes from the time signals take to travel between the player's computer and distant servers. Even moving at the speed of light, signals to servers on another continent can add tens of milliseconds of delay. This might seem trivial, but in fast-paced games, tens of milliseconds can mean the difference between victory and defeat. Financial markets have taken this to extremes. High-frequency trading firms spend millions of dollars to shave microseconds off their transaction times. They lay dedicated fiber optic cables along the shortest possible routes. They position their servers as close as possible to stock exchange computers. They exploit the finite speed of light to gain advantages measured in millionths of a second. The speed of light is not just an abstract limit in these contexts. It is a concrete constraint that shapes how business is done. Astronomy is, of course, deeply affected by the speed of light. When we look at the moon, we see it as it was about 1.3 seconds ago. The sun appears as it was 8 minutes ago. The nearest star beyond our sun, Proxima Centauri, shows us its state from over 4 years in the past. And the most distant galaxies we can observe are so far away that their light has been traveling for billions of years. We see them as they were when the universe was young, when our own sun had not yet formed, when Earth was still just a cloud of dust in an unborn solar system. This means that astronomy is also a form of time travel. Every image from a telescope is a window into history, Astronomers do not just study distant objects, they study the evolution of the universe across cosmic time. By looking at galaxies at different distances, they can see how galaxies have changed over billions of years. By studying the oldest light in the universe, the cosmic microwave background radiation that fills all of space, they can learn about conditions just a few 100,000 years after the Big Bang. The speed of light is what makes this time travel possible. Because light takes time to reach us, we can never see the universe as it is right now, but we can see it as it was at many different moments in the past. All simultaneously, the night sky is a gallery of history, with nearby stars showing the recent past and distant galaxies showing ancient eras. Each photon that enters your eye carries a message from a different epoch. The universe tells its own story through the light it sends us, and the speed of light is the narrator's pace. Consider the cosmic microwave background for a moment. This faint glow fills all of space, coming from every direction in equal intensity. It is the afterglow of the Big Bang itself, the remnant radiation from when the universe first became transparent to light, about 380,000 years after the beginning of time. Before that moment, the universe was so hot and dense that photons could not travel freely. They were constantly scattered by the soup of particles that filled all of space. But as the universe expanded and cooled, the particles combined into atoms, and suddenly light could stream unimpeded through the cosmos. The photons we detect as the cosmic microwave background have been traveling ever since. They have crossed 13.8 billion years of expanding space to reach our instruments. And they carry information about the universe as it was in its infancy, a time when galaxies did not yet exist, when the first stars had not yet ignited, when the cosmos was a nearly uniform sea of hydrogen and helium, with only the faintest ripples of density variation. Those tiny ripples would eventually grow into galaxies and clusters and superclusters. The cosmic microwave background is a baby picture of our universe, preserved in light and delivered to us by the constancy of the speed at which light travels. Feynman was born too early to see some of the most spectacular applications of these ideas. The detailed mapping of the cosmic microwave background came after his death in 1988. The discovery of the accelerating expansion of the universe came in 1998. The detection of gravitational waves, ripples in spacetime itself, came in 2015. Each of these discoveries confirmed and extended the theoretical framework that Feynman helped build, and each of them depended on the finite speed of light, which allowed us to observe distant events and piece together the history of the cosmos. But Feynman did live to see many wonders. He saw the first images from space telescopes orbiting above Earth's distorting atmosphere. He saw the detailed exploration of the planets by robotic spacecraft. He saw the development of lasers, devices that produce light so pure and concentrated that they can cut steel or measure the distance to the moon with incredible precision. Lasers work by stimulating atoms to emit photons in perfect synchrony, all moving in the same direction with the same frequency. The result is a beam of coherent light that can travel vast distances without spreading. Laser light sent to mirrors left on the moon by Apollo astronauts still returns to Earth after bouncing off those mirrors, allowing us to measure the moon's distance to within centimeters. All of this depends on the properties of light that we have been discussing: the constant speed, the quantum nature, the electromagnetic structure, the interaction with matter. These are not isolated facts to be memorized. They are threads in a tapestry that describes how the universe works at the most fundamental level. And Feynman was one of the master weavers who showed us how the threads connect. Let us rest here for a moment. Feel the stillness around you. Notice how the light in your room has been behaving perfectly according to the laws we have discussed. Photons streaming from your lamp, bouncing off walls and furniture, entering your eyes to create the scene you perceive. Every photon traveling at exactly the same speed, every interaction following the rules of quantum electrodynamics. The whole elaborate dance happening automatically, without effort, without thought, as it has been happening since the universe was young. There is a strange comfort in this reliability. The universe follows rules. It is not arbitrary or capricious. The same physics that governs the stars governs the candle on your nightstand. The same equations apply here and at the edge of the observable universe. There is unity beneath the diversity. There is order beneath the chaos. And the speed of light is one of the great unifying constants, the same everywhere and always, a fixed point in a changing cosmos. Now let us consider the future. What will humanity discover about light in the centuries to come? This is impossible to know, but we can speculate based on what we know now and what questions remain unanswered. One major frontier is quantum gravity. We have two great theories that describe the physical world. General relativity describes gravity as the curvature of space-time. Quantum mechanics and quantum field theory describe the other forces and the behavior of matter at small scales. Both theories work extremely well in their own domains, but they are incompatible with each other. When you try to apply quantum principles to gravity, you get nonsense answers full of infinities that cannot be removed. Physicists have been working on this problem for decades. String theory is one approach that attempts to unify quantum mechanics and gravity by imagining that all particles are actually tiny vibrating strings of energy. Loop quantum gravity is another approach that imagines space-time itself as woven from discrete loops, rather than being a smooth continuum. Neither approach has yet produced testable predictions that clearly favor it over the other. The problem remains open. What does this have to do with the speed of light? Everything. The speed of light emerges from the structure of space-time, from the way space and time are woven together. If quantum gravity changes our understanding of space-time at the smallest scales, it might change our understanding of the speed of light as well. Perhaps the speed of light is not perfectly constant at all scales. Perhaps at the Planck scale, where quantum gravity effects become important, the smooth space-time we know breaks down into something else entirely. Perhaps the concept of speed itself becomes meaningless when space and time lose their familiar definitions. These are deep questions for which we do not yet have answers, but the fact that we can ask them is remarkable. We are standing on the shoulders of giants like Feynman, looking toward horizons they could only imagine. The tools they gave us, quantum electrodynamics and the rest of modern physics, allow us to push further than they could go. And perhaps someone listening to these words tonight will one day help answer these questions. Perhaps the next great breakthrough in physics is sleeping in someone's mind right now, waiting to be awakened. Feynman would have loved this uncertainty. He often said that he preferred living with questions that could not be answered than with answers that could not be questioned. He distrusted certainty. He knew that science progresses by recognizing what we do not know and working to reduce our ignorance. The fact that we do not fully understand quantum gravity is not a failure. It is an invitation. It is a puzzle calling out to be solved. Let us now return to the original question that sparked this journey. Why is light speed the limit? We have circled this question many times tonight, approaching it from different angles. Now let us try to bring the threads together. The speed of light is the limit because space-time has a particular structure. That structure is described by the geometry of Minkowski spacetime in the absence of gravity, and by the curved geometry of general relativity when gravity is present. In both cases, the speed of light appears as a conversion factor between space and time, a fundamental constant that defines how the two dimensions relate to each other. The speed of light is the limit because accelerating a massive object requires energy, and the energy required grows without bound as you approach light speed. You would need infinite energy to push anything with mass all the way to the speed of light. Since infinite energy does not exist, massive objects can never reach that speed. The speed of light is the limit because causality requires it. If information could travel faster than light, you could send messages backward in time, creating paradoxes where effects precede causes. The universe appears to forbid such paradoxes. The speed of light is the boundary that keeps cause and effect properly ordered. The speed of light is the limit because the vacuum of space has definite properties, permittivity, and permeability that determine how fast electromagnetic disturbances can propagate. Light is such a disturbance. It moves at the speed the vacuum allows, and that speed turns out to be the universal speed limit. All these explanations are true simultaneously. They are different perspectives on the same underlying reality. The speed of light is woven into the fabric of physics at so many levels that it seems inescapable. Change it, and you change everything. The structure of atoms would be different. The chemistry of life would be different. Stars would burn differently. Time and space would relate differently. The entire character of the universe would transform. Perhaps this is why the speed of light is what it is. Perhaps in some deep sense, the speed of light had to be roughly what it is for a universe like ours to exist at all. This is a controversial idea, touching on questions about fine-tuning and the anthropic principle. Some physicists believe that the constants of nature, including the speed of light, could have been different, and we just happen to live in a universe where they allow complexity and life. Others believe the constants are somehow determined by deeper principles we have not yet discovered. Still others wonder if there are many universes with different constants, and we naturally find ourselves in one compatible with our existence. Feynman did not spend much time on such speculation. He preferred concrete calculations to metaphysical musing. But he appreciated the questions. He understood that physics borders on philosophy at its edges, and he had the wisdom to know that some questions might be beyond human capacity to answer. That did not trouble him. There was plenty to work on within the reach of our understanding. A lifetime was not enough to explore all the puzzles that could actually be solved. As you drift closer to sleep, let the mystery of the speed of light settle into your mind without demanding resolution. It is okay not to understand everything. It is okay to live with questions. The universe does not owe us explanations. That it gives us any understanding at all is a gift. And tonight, we have received many gifts. We have learned about Roma measuring light speed by watching Jupiter's moons. We have learned about Einstein realizing that the constancy of light speed implies the relativity of time and space. We have learned about Maxwell discovering that light is an electromagnetic wave. We have learned about Feynman showing how light and matter interact at the quantum level. These insights did not come easily. They took centuries of patient observation, bold theorizing, rigorous testing, and occasional lucky accidents. The history of physics is filled with wrong turns and dead ends. It is also filled with moments of breathtaking beauty when someone saw through the fog to a deeper truth. Feynman's development of quantum electrodynamics was such a moment. It brought together decades of confused partial results into a clear and coherent picture. It provided tools that physicists still use today. It earned him the Nobel Prize and secured his place in history. But Feynman did not care much about prizes and history. He cared about understanding. He would spend hours in his office, scribbling equations, drawing diagrams, muttering to himself. He would attack problems from every direction until they yielded their secrets. And when he succeeded, when he found an answer, he would feel a joy that no external recognition could match. The pleasure was in the figuring out, not in the acclaim that followed. This is perhaps the deepest lesson we can take from Feynman tonight. The value of understanding is not in what it gets you. It is in what it is. To know how light works, to grasp the equations that govern the universe, to see the connections that most people miss, this is its own reward. The speed of light is a mystery that humanity has pursued for centuries, and while we have learned much, there is still more to discover. The adventure continues, and you are part of it, even if only as a curious listener falling asleep to the sounds of cosmic wonder. Now let us venture into one more domain before we begin our slow drift toward the conclusion. We have talked about the speed of light in the context of physics and astronomy. Let us talk about it in the context of human experience. Light defines our perception of reality. Almost everything we know about the world comes through light. We see colors because light of different wavelengths stimulates different cells in our eyes. We perceive depth because our two eyes receive slightly different images, both carried by light, and our brains combine them into three-dimensional perception. We read books, watch screens, recognize faces, navigate landscapes, all through the medium of light entering our eyes. Our language reflects this primacy of vision. We speak of illumination as a metaphor for understanding. We call brilliant ideas enlightened. We describe confusion as being in the dark. We say that truth comes to light. These are not accidents. They reflect the fundamental importance of light in human experience. For most of our evolutionary history, light was the primary carrier of information about the world beyond our own bodies. But our experience of light is only a tiny slice of what light actually is. Human eyes detect wavelengths between roughly 400 and 700 nanometers. This is what we call visible light. But the electromagnetic spectrum extends far beyond these limits. Radio waves have wavelengths measured in meters or even kilometers. Microwaves have wavelengths of centimeters. Infrared light has wavelengths longer than red, reaching from about 700 nanometers to a millimeter. Ultraviolet light has wavelengths shorter than violet, from about 400 nanometers down to about 10 nanometers. X-rays and gamma rays have even shorter wavelengths, reaching down to the size of atomic nuclei. All of this is light. All of it travels at the same speed. All of it is governed by the same equations. The only difference is wavelength, which corresponds to energy. Shorter wavelengths mean higher energy. Gamma rays carry millions of times more energy per photon than radio waves. This is why gamma rays can damage cells and radio waves pass through us without effect. Energy matters. If our eyes could see all wavelengths, the universe would look utterly different. Radio telescopes reveal structures invisible to optical telescopes. They show the cold gas that fills galaxies, the remnants of ancient explosions, the microwave glow of the early universe. X-ray telescopes reveal the extremely hot gas around black holes, the violent collisions of neutron stars, the intense radiation from matter pushed to extremes. Infrared telescopes peer through dust clouds that block visible light, showing us the hidden nurseries where new stars are born. Modern astronomy uses all these windows on the universe. The James Webb Space Telescope observes primarily in infrared, allowing it to see through dusty nebulae and detect the light of the most distant galaxies, stretched into infrared by the expansion of space. The Chandra X-ray Observatory maps the violent high-energy processes that shape galaxies. The Atacama Large Millimeter Array listens to millimeter wavelength light, probing the cold molecular clouds where planetary systems form. Each window shows us a different aspect of cosmic reality, and all of it travels at the speed of light. This multi-wavelength astronomy was largely beyond Feynman's time. He knew the theory, of course. He understood that all electromagnetic radiation was fundamentally the same. But the technological explosion that allows us to observe so many different wavelengths with such precision came mostly after his death. He would have marveled at the images we have today. He would have immediately started asking what they meant, what new physics they might reveal, what questions they answered, and what new questions they raised. Feynman had an endless appetite for facts about the world. He did not only care about fundamental physics. He was curious about biology, about chemistry, about art and music and human culture. He learned to crack safes and play bongo drums. He visited places few physicists bothered to go, talking to people from all walks of life. He believed that physics was not separate from the rest of human knowledge. It was part of the same grand tapestry, and the threads connected in ways that were sometimes surprising. The speed of light connects to everything. It sets the pace at which information travels, which affects communication, coordination, and culture across the globe. It determines how we observe the universe, which affects our sense of our place in the cosmos. It constrains how fast we can explore, which affects our hopes and plans for the future. It shapes the structure of space-time, which determines the stage on which all events occur. Everything depends on this one number, this one constant, this one limit that the universe seems to enforce without exception. Yet here is something curious to consider as you rest. The speed of light in a vacuum is constant, but the speed of light in matter is different. When light passes through water, it slows down to about 75% of its vacuum speed. When it passes through glass, it slows to about 65%. When it passes through diamond, it slows to about 40%. The light is not really slowing down in the fundamental sense. Okay. What is happening is more subtle. The light is interacting with the atoms of the material, being absorbed and re-emitted over and over. These interactions take time, so the effective speed through the material is reduced. This slowing of light in matter leads to some beautiful phenomena. Refraction, the bending of light as it crosses from one material to another, happens because light changes speed at the boundary. Different colors refract by different amounts, which is why prisms spread white light into rainbows. The sparkle of a diamond comes from its high refractive index, which causes dramatic bending and splitting of light within the gem. And here is something strange. Particles can travel through matter faster than light travels through that matter. They cannot exceed the vacuum speed of light. But if light in water travels at 75% of its vacuum speed, a particle traveling at 80% of the vacuum speed is moving faster than light in that medium. When this happens, the particle produces a shock wave of light called Cherenkov radiation. It is the optical equivalent of a sonic boom. Nuclear reactors often glow with an eerie blue light because fast particles from the nuclear reactions are producing Cherenkov radiation in the water that surrounds and cools them. This does not violate anything. The vacuum speed of light remains the ultimate limit. but it shows that the behavior of light is subtler than a simple speed limit. The interactions between light and matter create a rich landscape of phenomena, from the blue of the sky to the colors of soap bubbles to the glow of a nuclear reactor. And all of it follows from the equations that Feynman and others developed. All of it is governed by quantum electrodynamics, the theory of light and matter interacting at the deepest level. Now let us move toward the climax of our journey. We have been circling the mystery of why light speed is the limit. We have seen many facets of this mystery, but there is one more perspective that might melt your mind in the way the title of this exploration promised. It concerns the nature of time itself. We tend to think of time as flowing smoothly and uniformly. 1 second follows another at a steady pace. The past is gone. The future is yet to come. The present is the thin knife edge between them, constantly advancing. This is how we experience time. But relativity suggests a different picture. In the relativistic view, time does not flow. Instead, all moments exist equally. The past, present, and future are all real. They are like different locations in space. Just as New York and Tokyo both exist right now, even though you cannot be in both places at once, yesterday and tomorrow both exist even though you cannot experience both times at once. Time is a dimension, just like space, and the universe is a 4-dimensional block containing all events that ever have happened or ever will happen. This is called the block universe or eternalism. It is a consequence of taking relativity seriously. Remember that different observers disagree about which events are simultaneous. If you and I are moving relative to each other, we will disagree about which events are happening right now at distant locations. There is no absolute present moment that everyone shares. My present might include events that are in your future. Your present might include events that are in my past. If the present moment is different for different observers, how can we say that only the present moment is real? We cannot single out one observer's perspective as the true one. All perspectives must be equally valid. And this leads to the conclusion that all moments are equally real. If this is true, then the speed of light takes on an even deeper meaning. It is not just a limit on how fast you can travel. It is a limit on how you navigate the 4-dimensional block of space-time. You are always moving through space-time at the speed of light. Yes, even right now, lying still, you are moving through space-time at exactly light speed. When you are at rest in space, all your motion is through time. You are racing into the future at 1 second per second. When you start moving through space, some of your motion through time gets redirected into motion through space. The total magnitude of your motion through space-time stays constant at the speed of light. You are always moving at light speed. You just choose, by your movement through space, how much of that speed is aimed toward the future and how much is aimed through space. This is perhaps the most mind-bending way to think about the speed of light. It is not external to you. You are traveling at that speed right now. You always have been. You always will be. The question is only which direction you are pointing in the 4-dimensional landscape of existence, and the geometry of space-time, with its peculiar mixing of space and time, determines what directions are possible. Photons represent an extreme case. They point entirely in spatial directions. All their motion is through space. None is through time. This is why photons do not experience time. They have no time component to their motion. They exist at a single moment from their own perspective, even as they cross billions of light years from ours. Photons are frozen in time, traveling forever through space at the universal speed. Contrast this with a massive object at rest. It has no motion through space. All its motion is through time. It races toward the future at the maximum possible rate, 1 second per second. When it starts moving through space, it trades some of its motion through time for motion through space. Its clocks slow down relative to a stationary observer. It ages more slowly. The faster it moves through space, the slower it moves through time, until at the limit of light speed, motion through time would stop completely, and only motion through space would remain. But massive objects cannot reach that limit. They can approach it asymptotically, getting closer and closer without ever arriving. They can trade more and more of their temporal motion for spatial motion, but they can never trade all of it. Some fraction of their motion must always remain pointed toward the future. This is why they can never reach light speed. This is why the limit exists. It is built into the geometry of how space and time are connected. Rest in this geometric picture. You are a traveler through space-time, always moving, at the speed of light, always carving a path through the four-dimensional block that contains all of history. Your choices about how to move through space determine how you move through time. The faster you walk, the slightly slower your clocks run. The effect is undetectable at human speeds, but it is real. Every step you take is a tiny trade, spatial motion for temporal motion. And if you could accelerate to near light speed, the trade would become dramatic. Years would pass for others, while only days passed for you. You would leap into their future while barely aging yourself. This is not science fiction. It is the geometry of reality. And it was Feynman's generation of physicists who fully understood how this geometry connects to the quantum behavior of particles and fields. They showed that the principles of relativity and quantum mechanics fit together, despite their apparent tension. They demonstrated that the speed of light emerges naturally from deep symmetries of nature. They gave us a coherent picture of reality that, while strange, is remarkably consistent and successful. Let this picture accompany you into deeper relaxation. You are made of atoms, which are made of electrons and nuclei, which interact through electromagnetic forces, which are mediated by photons, which travel at the speed of light, which is the conversion factor between space and time, which are woven together into the fabric of space-time, which contains all events past, present, and future. You are not separate from this cosmic structure. You are part of it. You are made of it. And understanding it, even a little, connects you to the universe in a way that ignorance never could. Feynman spoke often about the beauty of science. Not beauty in the superficial sense of pretty pictures, though physics has those too. Beauty in the deeper sense of elegant connections, surprising unifications, simple principles that explain complex phenomena. The speed of light is beautiful in this sense. It seems so simple, just a number. But trace its implications and you find it connected to time dilation, length contraction, mass-energy equivalence, the structure of space-time, the behavior of electromagnetic fields, the quantum mechanics of photons, the impossibility of faster-than-light travel, the boundaries of the observable universe, and so much more. One number woven through almost everything physics studies. This interconnection is what makes physics so powerful. You do not need separate theories for every phenomenon. A small number of fundamental principles, properly understood, explain a vast range of experience. The speed of light is one of those fundamental principles. Understand it, and doors open throughout physics. Misunderstand it, and confusion follows you everywhere. Feynman knew this. His teaching, perhaps even more than his research, emphasize the importance of truly grasping fundamentals rather than memorizing formulas. Now let us begin the gentle descent toward conclusion. We have traveled far tonight. We have visited the laboratories of Ole Rømer, watching Jupiter's moons, the patent office where Einstein dreamed of chasing light beams, the university offices where Feynman drew his famous diagrams. We have contemplated the relativistic effects of high-speed travel, the quantum nature of photons, the structure of spacetime itself. We have asked why nothing can exceed the speed of light, and found answers in geometry, in energy, in causality, in the very definition of what time and space mean. But perhaps the deepest answer is simply this. The speed of light is what it is because that is how our universe works. It did not have to be this way. We can imagine universes with different physics, different constants, different limits. But those imaginary universes are not our home. We live here in this universe with this speed of light. And this speed of light has made possible everything we know. Stars that burn steadily for billions of years, planets where complex chemistry can unfold, life that can evolve and contemplate its own existence, minds that can ask why the speed of light is the limit. We are not outside the universe, observing it from some neutral vantage point. We are inside it, made of it, constrained by it. The speed of light that limits how fast we can travel is the same speed of light that allows the stable atoms of our bodies to exist. The causality that prevents us from sending messages backward in time is the same causality that allows us to make plans and see them succeed. The limits are not punishments. They are the conditions that make existence possible. Feynman understood this too. He did not rage against the limits of physics. He explored them, mapped them, found their consequences both profound and practical. He saw that the constraints of nature are also the scaffolding of nature. Without those constraints, there would be nothing. No structure, no pattern, no meaning, just chaos without form. The speed of light is part of what gives form to our universe. It is part of what makes the universe a place where anything can happen at all. So as you drift towards sleep, do not think of the speed of light as a prison wall. Think of it as the frame of a house. The frame is not a barrier to living in the house. It is what makes the house possible. The rooms you inhabit, the views from your windows, the shelter from the storm, all depend on the frame holding everything together. The speed of light frames our universe. It holds together the structure of space-time. It makes possible the room we call reality. And within that room, there is so much to explore. Even with the speed of light limit, the accessible universe is mind-bogglingly large. Our own solar system, with its diverse worlds and moons, would take lifetimes to fully explore. The nearest stars, though unreachable in a single human lifetime with current technology, might someday receive our robotic ambassadors, carrying messages and memories across the light years. And within the grasp of our instruments, we can observe and study galaxies billions of light years away, learning about the evolution of the cosmos across nearly all of its history. The limit is not an ending, it is a beginning. It defines the playing field on which all our adventures occur, and it challenges us to be creative, to find ways to accomplish our goals within the constraints we face. The greatest achievements often come not from removing constraints, but from working with them skillfully. Feynman's genius was not in breaking the rules of physics. It was in understanding the rules so deeply that he could dance within them, finding possibilities that others had missed. Now let the light in your room settle into softness. Notice how it fills the space without effort, without noise. Every photon traveling at 292,458 meters per second, bouncing off surfaces, entering your eyes, creating the scene you perceive. This happens automatically, reliably, constantly. The laws of physics never take a day off. The speed of light is the same tonight as it was at the birth of the universe. The same principles that govern light in distant quasars govern the light beside your bed. There is a strange comfort in this constancy. The universe may be vast and indifferent, but it is not arbitrary. It follows rules. It behaves consistently. What works here works everywhere. What was true yesterday will be true tomorrow. This reliability is not exciting in the way of surprises and plot twists, but it is deeply reassuring. You can count on the universe. It will not change its rules while you sleep. The light will still travel at light speed when you wake. The atoms of your body will still hold together according to quantum electrodynamics. The ground beneath you will still push back against gravity. The ordinary miracles will continue, uninterrupted, unnoticed, indispensable. Feynman found joy in these ordinary miracles. He once wrote about the pleasure of figuring out that the redness of a sunset comes from the same physics as the blueness of the sky. Both involve light scattering off molecules in the atmosphere. Blue scatters more than red, so blue light bounces around the sky, while red light continues straight. When you look at the sky away from the sun, you see the scattered blue light. When you look toward the setting sun, you see the red light that made it through without scattering. Same physics, two beautiful phenomena. This is what understanding brings, not the cold dissection of beauty into dull components, but the multiplication of beauty by revealing its connections. The sunset is not less beautiful for being explainable. It is more beautiful for being connected to the scattering of light, which is connected to the electromagnetic interaction, which is connected to quantum electrodynamics, which is part of the grand structure of physical law. The threads run everywhere, connecting everything. And the more threads you can see, the richer the tapestry appears. We have followed many threads tonight. The thread of measurement, from Romer's observations of Jupiter's moons to modern atomic clocks. The thread of theory, from Maxwell's equations to Einstein's relativity to Feynman's QED. The thread of implication, from time, dilation to the observable universe to the block nature of spacetime. The thread of wonder, from the question of why to the acceptance that some questions may have no final answer. All these threads are woven around the speed of light. It is the common element, the recurring motif, the thing that connects the beginning of our story to its end. Why is light speed the limit? Because it is built into how space and time relate. What did Feynman uncover? That light is quantum in nature, that its interactions with matter can be calculated with unprecedented precision, that the speed of light emerges from the deep symmetries of physics. Will this melt your mind? Perhaps. The ideas are strange enough to disturb our everyday intuitions, but they are also beautiful enough to reward the disturbance. Now let the strangeness settle. Do not try to hold all these ideas in your mind at once. Let them drift and mingle like clouds in a summer sky. Some will stay with you. Some will fade until you revisit them. The purpose of this journey was not to fill your head with facts to be memorized. It was to shift your perspective, even slightly, to help you see the light around you with new eyes, to connect you with the great minds who have wondered about these questions, to bring you into the conversation that humanity has been having about the nature of reality for centuries. You are part of that conversation now. Even if you never think about physics again, something of tonight will remain with you. The next time you see a beam of sunlight or a star in the night sky, some part of you will remember that the light traveled a long way to reach you at exactly 299,792,458 meters per second, carrying information about its source across time and space. Some part of you will remember that nothing can travel faster, that causality itself respects this limit, that the structure of the universe depends on it. Some part of you will feel the strangeness and the wonder that Feynman felt when he first understood these things. And that is enough. That small shift in awareness is precious. It connects you to something larger than yourself, not just the physical universe, though that too, but the community of curious minds across history who have asked the same questions you are asking tonight. The astronomers who mapped the heavens, the physicists who wrote the equations, the philosophers who pondered the implications, the children who looked up at the stars and wondered. You are part of this family. You belong to the great human project of understanding our world. Feynman belonged to this family in a special way. His contributions to physics were enormous, but perhaps his greatest contribution was his attitude. He showed that science could be joyful. He showed that the deepest questions could be approached with playfulness. He showed that admitting what you do not know is not weakness but honesty. He showed that the universe rewards those who pay attention, who ask questions, who refuse to accept superficial answers. Tonight we have paid attention to the speed of light. We have asked why it is the limit. We have refused to accept the simple answer that it just is. And in return, the universe has rewarded us with glimpses of its structure. Time that bends, space that contracts, mass that increases, causality that holds, photons that explore all paths, spacetime that contains all moments. These glimpses are not the whole truth. There is always more to learn, but they are genuine glimpses. They are not illusions or metaphors. They are descriptions of how reality actually works, tested by experiment, refined by theory, confirmed to extraordinary precision. This is real knowledge about the real world, and it is available to anyone who wants it. So take what you have received tonight and let it rest within you. Do not force it. Do not strain to remember every detail. Just let the atmosphere of wonder suffuse your awareness. You have contemplated deep mysteries in the quiet of this hour. You have traveled in imagination to the edges of the observable universe and to the quantum depths of light and matter. You have walked for a while with Feynman, seeing through his eyes. And now you can return to your own eyes, enriched by the journey. The light continues around you. Photons stream through your room, carrying their messages, obeying their laws. The universe continues outside, vast and patient, filled with wonders you have not yet discovered. And time continues, carrying you gently toward sleep, toward tomorrow, toward whatever adventures await, all at the pace allowed by the speed of light, all within the framework that makes existence possible, all part of the great story that physics tells. Sleep well, traveler. The universe will keep its secrets until you are ready to explore again. The speed of light will still be waiting when you wake, and so will the wonder if you remember to look for it. But before you close your eyes completely, let us spend a little more time together. There is still ground to cover, still thoughts to share, still the slow unwinding toward final rest. We have reached a plateau in our journey, but the path continues gently downward from here. Let us talk about light as a communicator. We have said that light carries information, but what kind of information? What can light tell us? Light tells us about the objects that emit it or reflect it. When you see a tree, the light entering your eyes carries information about the tree's shape, color, and position. Your brain interprets this information and constructs a mental model of the tree. This happens so automatically that we do not notice the complexity involved. But it is remarkable that electromagnetic radiation, traveling through empty space, can encode detailed information about distant objects and deliver it to receivers like our eyes. Astronomers exploit this information-carrying capacity to study objects they will never touch. The light from a star tells them its temperature, its composition, its motion, its age. These properties are encoded in the spectrum of the light, the pattern of colors and their intensities. Hot stars emit more blue light than red. Cold stars emit more red than blue. Atoms in the star's atmosphere absorb specific colors, leaving dark lines in the spectrum that identify the elements present. The overall shift of these lines toward red or blue reveals whether the star is moving toward us or away. A single beam of light can carry all this information and more. The photons arrive at our telescopes as messengers from afar, each one carrying a tiny piece of the puzzle. Combine enough photons, and you can build a detailed picture of what is happening at the source. This is how we know that the Sun is made mostly of hydrogen and helium. This is how we know that galaxies contain billions of stars. This is how we know the universe is expanding. The speed of light determines how fresh this information is. The light from the Sun shows us the Sun as it was 8 minutes ago. Light from nearby stars shows them as they were years ago. Light from distant galaxies shows them as they were billions of years ago. We cannot see the present state of anything outside our immediate vicinity. We only see the past. The farther away something is, the deeper into the past we are looking. This creates a peculiar kind of isolation. We are cut off from the present moment of the distant universe. Whatever is happening right now at a star 10 light years away, we will not know about it for 10 years. Whatever happened there 10 years ago, we are only learning about it now. And because the universe is expanding, most of the galaxies we see are now farther away than they were when they emitted the light we are detecting. Some have been carried so far by expansion that their light, stretched to invisibility, will never reach us again. Yet within this isolation, we have built remarkable connections. The Voyager spacecraft, launched in 1977, carry messages from Earth into interstellar space. They bear golden records with sounds and images of our planet, greetings in many languages, music from many cultures. These records travel at the speed of Voyager, only about 17 kilometers per second, far slower than light. But they carry the hope that someday, somewhere, someone might find them and know that we existed. More ambitiously, we send radio signals into space deliberately. The Arecibo message, transmitted in 1974, was aimed at a cluster of stars 25,000 light-years away. If anyone there receives and responds, their reply will not arrive for 50,000 years. We will not be here to receive it. Our descendants, if we have descendants, might hear it. Or the message might vanish into the void, unheard. The speed of light makes interstellar conversation almost impossible. By the time a reply arrives, the civilization that sent the original message might have transformed beyond recognition or vanished entirely. This is the loneliness of the cosmic speed limit. We can see countless stars and galaxies. We can infer that planets abound. We might even, someday, detect signs of life on other worlds. But we are unlikely ever to have a real-time conversation with beings from another star system. The light-speed barrier makes the universe observable, but largely unreachable. We are watchers more than participants in the cosmic drama. Yet there is something grand in this watching. We are the universe becoming aware of itself, We are matter contemplating matter. Through our eyes and instruments, the cosmos sees its own face. And even if we cannot touch the distant stars, we can understand them. We can trace their life cycles. We can predict their futures. We can locate them in the vast web of cosmic evolution. Understanding is a form of connection that distance cannot break. Feynman felt this connection deeply. He spoke about the thrill of realizing that the atoms in his body were forged in ancient stars. Carbon from supernovae, iron from stellar cores, oxygen from the fusion reactions that power suns. We are literally made of star stuff. The light that carries information across the cosmos is the same light that those ancient stars once emitted. We are related to those stars in the most physical sense possible. This cosmic perspective was important to Feynman. He believed that science should not shrink our sense of significance but expand it. Yes, we are small compared to the universe. Yes, we exist for only a brief moment in cosmic time. But we are part of the same process that created galaxies and ignited stars. We are expressions of the same laws that govern the most distant quasars. Our atoms will one day return to the cosmic cycle, joining the clouds that will form new stars and new planets and perhaps new forms of life. The speed of light connects all of this. It carries the energy from stars to planets, enabling life. It carries the information that allows minds to form understanding. It sets the rhythm of cosmic evolution, the pace at which structure can grow and change. Without this speed, there would be no us to wonder about it. The same limit that constrains us also created us. We are children of the light-speed universe. Now let us sink even deeper into stillness. The night deepens around you. The concerns of the day recede. The mysteries we have explored tonight begin to blur at the edges, becoming not puzzles to be solved, but atmospheres to be inhabited. This is how the journey ends. Not with answers, but with presence. Not with conclusions, but with openness. The speed of light remains. It will be there when the last star burns out. It will be there in the cold, dark future, when galaxies have flown apart beyond each other's horizons. Even then, photons will travel at exactly 299,790,458 meters per second, carrying whatever faint energy remains across the ever-expanding void. The universe may change beyond recognition, but its deepest laws will persist. And the speed of light is one of those deepest laws. We have traveled tonight with a remarkable guide. Richard Feynman died in 1988, but his ideas live on. His diagrams adorn physics textbooks around the world. His approach to understanding, building up from basic principles with honesty and playfulness, inspires new generations of scientists. And his insistence that the joy of finding out is the deepest reward of inquiry echoes in classrooms and laboratories everywhere. What would Feynman say if he could see how far physics has come since his death? He would probably ask sharp questions. He would demand to understand the new ideas from the ground up. He would find errors that others had missed and connections that others had ignored. And he would delight in the continuing mystery, the fact that despite all our progress, the universe still holds secrets. The speed of light holds secrets too. We know so much about it, and yet deep questions remain. Why this particular value? Why not a little faster or a little slower? Is it truly constant at all scales, or does it fluctuate at the Planck scale where quantum gravity rules? These questions may have answers, or they may not. The universe does not guarantee that every question has an answer we can find. But the asking is still valuable. The wondering still connects us to something larger. Whether or not we solve every puzzle, we participate in the great human adventure of inquiry. We add our small contributions to the tapestry of understanding. We pass on what we have learned to those who come after. This is how knowledge grows. This is how civilizations mature. And this is how individuals like you, listening to these words in the quiet of the night, join the ongoing conversation about the nature of reality. So consider yourself a participant now. You have heard tonight about the speed of light, about relativity and quantum mechanics, about Feynman and his contributions, about the structure of spacetime and the boundaries of the observable universe. This knowledge is yours to keep or set aside as you choose, but some trace of it will remain, some widening of perspective, some sense of the strangeness and wonder that lies behind ordinary experience. That is the gift of physics, not just facts and equations, though those matter, but a way of seeing, a posture toward the world, an appreciation for how deep the mysteries run and how remarkable it is that we can understand anything at all. Feynman embodied this gift. He gave it freely to his students and to readers of his books, and it spreads from person to person, across generations, carried by the slow relay of teaching and learning. You are part of that relay now. Perhaps you will share what you learned tonight with someone else. Perhaps they will share it further. The ideas ripple outward, like light itself, at whatever pace circumstances allow, and eventually they touch minds that would never have encountered them otherwise. This is how understanding propagates through a civilization, slowly, imperfectly, but persistently. The light in your room is dimming now, either actually or metaphorically, as sleep approaches. Let the photons grow softer. Let the questions grow gentler. You have worked hard tonight, following these thoughts across billions of light years and into the quantum depths. Now it is time to rest. The universe will continue its workings while you sleep. The stars will keep burning, the galaxies will keep turning, the light will keep traveling, and you, made of atoms that were once in stars, will drift into the ancient renewal of sleep. But before we part entirely, let us gather a few final thoughts. Consider this. The speed of light is not just a fact about physics. It is a fact about possibility. It tells us what can happen and what cannot. It draws boundaries around the future. Not harsh boundaries that crush all hope, but structural boundaries that give shape to what we can become. Within these boundaries, much remains possible. We can explore our solar system. We can send robots to other stars, even if we cannot follow quickly ourselves. We can send and receive signals across light years, participating in a slow-motion conversation that might span generations. We can understand the universe even if we cannot touch all of it. We can find meaning even in a cosmos that dwarfs us beyond comprehension. The speed of light teaches us to be patient. It teaches us to plan on long timescales. It teaches us that some journeys cannot be rushed. These are not easy lessons for a species evolved to survive immediate threats and grasp immediate opportunities, but they are lessons worth learning. The universe is patient. Perhaps we can learn to be patient too. Feynman was patient in his own way. He would spend weeks or months on a problem, approaching it from different angles, waiting for insight to strike. He knew that understanding cannot be forced. It emerges in its own time, often when you stop grasping and simply pay attention. This patience served him well. It allowed him to see things that hurried minds had missed. It allowed him to make contributions that will last for centuries. Perhaps patience is what the speed of light is really teaching us. Not frustration at what we cannot do, but acceptance of the pace at which deep things unfold. The universe took billions of years to make stars and planets and life. It will take billions more to reach its final state, whatever that may be. Against such timescales, our hurry seems almost comical. We rush through our days as if there was something to catch, when the cosmos moves at its own stately tempo regardless of our urgency. Rest now in that cosmic tempo. Feel the slow rotation of the Earth carrying you through the night. Feel the Earth itself orbiting the Sun, completing one circle per year, moving at about 30 kilometers per second. Feel the Sun moving through the galaxy, taking 230 million years to complete one orbit. Feel the galaxy moving through the expanding universe, carried by the overall flow of cosmic evolution. All of this motion is happening right now, as you lie still. All of it follows the laws we have discussed tonight. All of it unfolds at its own pace, unhurried by human anxiety. The speed of light is fast by human standards. 209,792,458 meters per second is far beyond anything we can achieve with our bodies or our machines. But compared to the size of the universe, it is remarkably slow. Light takes years to reach the nearest stars, millennia to cross the galaxy, billions of years to traverse the observable universe. The cosmos is so large that even light, the fastest thing there is, seems to crawl across its expanse. Distance defeats speed. The universe is bigger than fast. This puts us in a peculiar position. We have discovered the speed limit. We understand why it exists. We have measured it with exquisite precision. And yet we are utterly incapable of approaching it. Our fastest spacecraft travel at tens of kilometers per second, barely a few hundredths of 1% of light speed. To reach even 1% of light speed would require transformative technologies we do not yet possess. And even at 1%, the nearest star would take over 400 years to reach. Perhaps this limitation is not accidental. Perhaps the universe is structured so that beings like us, emerging on planets around stars, are largely confined to their home systems. Perhaps interstellar civilizations are rare or impossible, not because intelligent life is rare, but because the speed of light makes expansion so slow and difficult. Or perhaps civilizations that last long enough eventually find ways we cannot yet imagine. We simply do not know. The speed of light sets the rules, but the story is still being written. What we do know is that we are here now, in this moment of cosmic history. We are aware. We are curious. We are capable of understanding at least some of what surrounds us. And the speed of light, this limit that defines so much, is part of what makes our existence possible. Without a speed limit, without the causal structure that the speed of light enforces, there might be no stable atoms, no lasting structures, no evolution of complexity, no minds to contemplate the cosmos. The limit is also a gift. Let this reframing settle into your awareness. The speed of light is not an obstacle between you and the stars. It is the framework that allows there to be a you and allows there to be stars in the first place. It is the boundary that makes the space inside meaningful. Like the banks of a river that give the water somewhere to flow, the speed of light gives the universe somewhere to unfold. Feynman saw physics as a story about patterns and connections. The speed of light is one of the most important patterns. It connects time to space, energy to momentum, cause to effect. It appears in equations that describe everything from the flight of photons to the bending of spacetime around black holes. It is a golden thread running through the tapestry of physical law. Following that thread has taken us far tonight. We began with a simple question. Why is light speed the limit? We have found answers in relativity, in quantum mechanics, in the structure of spacetime itself. We have met Feynman and glimpsed his approach to physics. We have contemplated the observable universe and our place within it. We have wondered about the future and accepted the uncertainty that surrounds it. Now the thread leads to rest. The journey tonight is nearly complete. The light outside has shifted, or perhaps your eyes have grown too heavy to notice. The words are softer now, closer to whispers. The ideas have done their work. They have planted seeds that may or may not grow, depending on the soil of your attention. That is how learning works. You cannot force it. You can only create conditions and wait. So wait now, in the gathering stillness. Let the speed of light recede into abstraction, a number among numbers, a fact among facts. You do not need to hold on to it. It will be there when you need it. The universe holds its patterns in place without your effort. Your only task now is to let go, to surrender to the darkness that brings sleep, to trust that the light will return when you wake. The photons will still be there tomorrow. The sun will send them across 93 million miles of space, and they will arrive 8 minutes later, traveling at exactly the speed they have always traveled. Some will warm your skin. Some will enter your eyes and bring you news of the world. And somewhere in your mind, perhaps too faint to notice, will be the memory of tonight, when you learned why that speed is the limit, what Feynman uncovered about the nature of light, and how the structure of reality is more strange and beautiful than ordinary experience suggests. That memory is itself a form of light. It carries information. It connects you to the minds that discovered these truths. It links your small life to the vast processes that govern galaxies and atoms alike. You are not separate from the cosmos. You are a piece of it that has awakened and looked around and asked questions. And the questions you ask are among the most profound any mind can contemplate. Why is there something rather than nothing? Why does the universe follow laws? Why are those laws mathematical? Why is there a speed limit? These questions may never have final answers, but asking them is itself an achievement. It means that the universe has produced beings capable of reflection, capable of wonder, capable of reaching beyond the immediate to grasp the eternal. You are such a being. Tonight you have exercised that capacity, and now you can rest, knowing that the capacity will still be there tomorrow. The light fades, the night deepens, the stars continue their ancient burning, indifferent to our thoughts, but available to our wonder. Somewhere in the distant cosmos, photons are beginning journeys that will end billions of years from now, carrying information about events we will never witness. Somewhere else, photons are arriving after journeys that began before Earth existed. The universe is a web of light, connecting all places and all times within the boundaries the speed of light allows. You are caught in that web, gently held like a dewdrop on a spider's silk. The threads extend in all directions, binding you to everything else. You cannot break free, and why would you want to? To be part of this web is to be part of existence itself. The speed of light is one of the threads, perhaps the most important one. It determines the shape of the web, the patterns it can form, the stories it can tell. Tonight, one small thread has vibrated with the story of light and its speed. The vibration has reached you. It has shaken something loose in your understanding, or perhaps simply confirmed something you already sensed. Either way, the connection is made. You are a little more woven into the cosmic pattern than you were before. And now, rest. The pattern will hold without your attention. The speed of light will remain exactly what it is. The universe will continue its workings, patient and implacable. And you, tired traveler, will drift into the darkness where thought dissolves, and the body heals, and the next day prepares itself in silence. May your dreams be gentle, may your sleep be deep, and may you wake with a flicker of wonder, a trace of the mystery that we explored together tonight. The speed of light will be waiting, constant as ever, ready to carry the first photon of morning to your opening eyes. Good night, curious mind. The cosmos thanks you for your attention, and somewhere, in the quantum foam that underlies all existence, Feynman is still scribbling his diagrams, still asking his questions, still delighting in the game of finding out. His spirit lives on in everyone who wonders about the nature of things, including you. The journey ends here, but only for tonight. Tomorrow, there will be more questions, more mysteries, more opportunities to follow the threads that connect everything to everything else. The speed of light will be part of many of those journeys. It cannot be escaped. But perhaps now you will see it differently. Not as a barrier, but as a foundation. Not as a limit, but as a law. Not as a frustration, but as a feature of the beautiful universe that somehow produced you and allowed you to ask why. Sleep now. The light will keep its secrets safe until you are ready to explore again. But wait, just a little longer. There is more stillness to find, more darkness to sink into. Let us linger here at the edge of sleep, where thoughts become dreams and dreams become rest. The words are almost done. Just a few more to carry you the final distance. Think once more about light, not the physics of it now, but the experience. The way morning light falls through a window, painting rectangles of gold on the floor. The way moonlight silvers a landscape, transforming the familiar into the strange. The way candlelight flickers, creating shadows that dance on the walls. The way starlight, ancient beyond measure, pricks the darkness with tiny promises. Light is more than photons. It is part of how we know we are alive. The speed of light determines how all that beauty reaches us. Without that speed, without the electromagnetic interactions that produce it, without the quantum mechanics that underlies it, there would be no sunrises to watch, no candles to light, no stars to wish upon. The physics we have explored tonight is not separate from poetry. It is what makes poetry possible. Feynman understood this unity. He wrote once that poets say science takes away from the beauty of the stars, seeing them only as gas balls and nothing more. But he could see more than poets could. He could see the vast machinery of the heavens, the nuclear furnaces burning for billions of years, the long travels of light across the emptiness, the evolution of stars from birth to death. He found this knowledge did not detract from beauty but added to it. The poetry was enhanced, not diminished. Let that enhancement be yours as well. The next time you see light, let a whisper of tonight's journey accompany your perception. Remember that the light you see has traveled, perhaps for years, perhaps for billions of years, at exactly 219,792,458 meters per second. Remember that it cannot go faster, that nothing can, that this limit shapes the entire structure of reality. Remember Feynman drawing his diagrams, showing how photons dance between particles. Remember that you are made of atoms that once shone in stars. Let all of this deepen rather than diminish the beauty you perceive. The night grows older. Your breathing has slowed. The tension in your muscles has eased. The words are becoming harder to follow, and that is good. It means sleep is close. Soon the conscious mind will release its grip, and you will drift into the restorative darkness where the body repairs itself and the mind processes the day's experiences. Perhaps you will dream of light. Perhaps you will soar through the cosmos, riding a beam of sunshine to the outer planets. Perhaps you will shrink to the size of an atom and watch photons zip past, each one a blur of speed beyond comprehension. Perhaps you will stand beside Feynman in a dream lecture hall, watching him explain the mysteries with his characteristic enthusiasm. Or perhaps your dreams will have nothing to do with physics at all. That is fine too. The learning has happened. The seeds are planted. What grows from them is not entirely up to you. The universe is full of such mysteries. We know so much, and yet we know so little. The speed of light is one of the best measured quantities in all of physics, known to 9 decimal places. Yet we do not fully understand why it has the value it does. We can describe how it emerges from the properties of spacetime, from the vacuum, from fundamental constants. But we cannot explain why those fundamental constants have the values they do. At some point, description gives way to acceptance. The universe is what it is. Our task is to learn its patterns, not to demand justifications it does not offer. This acceptance is part of scientific maturity. Young scientists often expect nature to make sense in human terms, to have reasons we can understand and approve. Mature scientists learn that nature simply is, and our approval is irrelevant. The speed of light does not exist to please us or frustrate us. It exists because space-time has a particular structure. Our job is to discover that structure, not to judge it. Feynman had this maturity. He was content to know how things worked without always knowing why they worked that way. He distrusted the demand for ultimate explanations. He preferred working explanations, answers that connected phenomena and made predictions, even if they left deeper questions open. This pragmatic approach allowed him to make progress where others got stuck in philosophical tangles. Perhaps you can adopt some of that pragmatism. Accept that the speed of light is what it is. Marvel at its consequences. Use the knowledge to deepen your understanding of the universe. But do not demand that the universe justify itself to you. It will not. And that is okay. There is still plenty of wonder in the what and the how, even if the why remains elusive. The stillness deepens. The last thoughts are fading like stars at dawn. The speed of light recedes into the background of consciousness, taking its place among all the other things you know, but do not constantly think about. It will resurface when needed, when some observation or question brings it back to attention. For now, it can rest along with you. Tomorrow, the world will continue. People will go about their business, mostly unaware of the speed of light, mostly focused on immediate concerns. That is how it must be. We cannot walk around in a constant state of cosmic wonder. The mind would exhaust itself. Wonder is for moments like these, quiet interludes when the ordinary fades and the extraordinary becomes visible. You have had such a moment tonight. You have contemplated the speed of light and what it means for reality. You have traveled with Feynman into the quantum world. You have considered the boundaries of the observable universe and your place within it. These thoughts will settle into memory, most of them forgotten, some retained, a few perhaps to resurface at unexpected moments and surprise you with their continued presence. That is how learning works across a lifetime. You accumulate experiences, most of which fade, but each of which contributes something to the overall shape of your mind. Tonight's journey will contribute its part. Perhaps it will make you a little more patient, a little more accepting of limits, a little more appreciative of the structure that makes existence possible. Or perhaps it will simply give you a fact to share at a dinner party someday. Did you know that nothing can travel faster than light? And here is why. Either way, the time has been well spent. The universe has shared a piece of itself with you. You have accepted the gift, And now the gift giver and the receiver can part for the night, each returning to their own domain of existence. The last light is fading now, not the physical light perhaps, but the light of attention that has illuminated these ideas. The spotlight is dimming. The stage is emptying. The audience of your conscious mind is leaving the theatre. Soon only the janitors of the unconscious will remain, sweeping up the day's debris, preparing for tomorrow's performance. Let them work in peace. Let your conscious self retreat to wherever it goes during sleep. Let the body take over, doing its quiet miracles of maintenance and repair. Let time pass without counting it. Let the earth turn without feeling it. Let the cosmos wheel overhead without watching it. All of this will happen whether you attend to it or not. The speed of light will remain exactly what it is. The photons will travel their paths. The laws of physics will hold. You do not need to supervise. You can simply rest. And in that rest, perhaps, some small integration will occur. The ideas of tonight will weave themselves into the fabric of your understanding. The speed of light will find its place alongside all the other things you know about reality. And when you wake, you will be slightly different, slightly expanded, slightly more connected to the universe that contains you. This is what learning does. It changes us. It makes us more than we were. The change is usually too small to notice, but it accumulates over years and decades. The person you are today is the sum of all your learning, including tonight's. And the person you will become depends partly on what you learn from here forward. The speed of light will be part of that future self, however faintly, however indirectly. So go now into sleep with gratitude. Gratitude for the light that fills our world. Gratitude for the minds that uncovered its secrets. Gratitude for the capacity to wonder, to question, to learn. Gratitude for the rest that restores you and prepares you for another day of living. These gratitudes need not be articulated. They can simply be felt, a warmth beneath the surface of consciousness, a background hum of appreciation. The speed of light has been our companion tonight. We have learned why it is the limit, what Feynman discovered about its nature, how it shapes the universe we inhabit. We have traveled far on the wings of thought. And now, those wings are folding. The journey is truly complete. Before the final silence descends, let us pause once more to appreciate what we have touched upon. We have entered territory that the greatest minds in history have explored. We have walked the same conceptual paths that Einstein walked when he imagined chasing a beam of light. We have glimpsed the same quantum strangeness that Feynman spent his life illuminating. We have confronted the same cosmic vastness that has humbled every observer who looked up at the stars. This is the inheritance of being human in the age of science. We have access to understanding that previous generations could not have dreamed of. We know the approximate age of the universe. We know the composition of stars. We know the structure of atoms. We know the speed of light. These represent the accumulated effort of countless curious minds across the centuries, each adding their piece to the puzzle. And you are now a recipient of that inheritance. You have received a tiny fraction of what humanity has learned about the cosmos. But even that fraction connects you to the whole. It places you in the conversation that began when the first humans looked up at the night sky and wondered what the lights were. That conversation has evolved over millennia, growing more precise, more mathematical, more strange. But it remains fundamentally the same conversation. What is this universe we find ourselves in? How does it work? Why does it work that way? The speed of light is one answer to those questions. It tells us that the universe has structure. It tells us that not everything is possible. It tells us that causality matters, that cause must precede effect, that time has a direction. These are profound truths about the nature of existence. And now you carry them with you, however lightly, however imperfectly. Feynman would be pleased, perhaps, to know that his ideas are still being shared, still inspiring wonder. He wanted physics to be accessible. He believed that the deep truths of nature belong to everyone, not just specialists with advanced degrees. He spent enormous effort translating complex ideas into language that ordinary people could grasp, and his legacy continues in every popularization of physics, including this one. So thank Feynman, silently, for his contribution to your understanding tonight. Thank Einstein and Maxwell and Romer and all the others who built the framework we have explored. Thank the teachers who taught them and the students they taught in turn. This is a collective achievement, stretched across time and space, woven from countless individual contributions. And tonight, you have added one more thread, however small, by paying attention and letting the ideas enter your mind. The thread you add is your own unique personal understanding. It may not advance physics, it may not produce new equations, but it makes the tapestry a little larger. Every mind that grasps these ideas adds to their reality. Every person who understands why the speed of light is the limit helps that understanding persist. Knowledge is fragile. It exists only in minds, and every new mind that holds it makes it more secure. You are now such a mind, one of billions who know something about the speed of light. But still, you count. Your understanding matters. It connects you to all the other minds who share this knowledge. It makes you part of the great human project of comprehension, the slow accumulation of insight. The darkness welcomes you, the silence holds you, the night enfolds you, and somewhere at 299,792, 458 meters per second, the light continues its eternal travels, connecting everything to everything else, weaving the cosmos into a single fabric that includes your dreams and your waking, your questions and your rest. Good night. Sleep well. And when you wake, may the light be waiting for you, unchanged and unchangeable, ready to begin another day of the endless journey through space-time that we call life. The end, or rather, a pause, for there is no end, not really. Only the ongoing unfolding of a universe that moves at the pace its structure allows, carrying us with it into whatever comes next. Rest now in that flow. Trust that the flow knows what it is doing. It has been at this for nearly 14 billion years. It has made galaxies and stars and planets and life. It will continue long after we are gone, and the speed of light will be there through all of it, the faithful constant, the universal limit, the thread that holds the tapestry together. May you dream of light, and may you wake to light, and may your journey be filled with wonder.